Hi, everybody. Really nice to be speaking at an in-person event after COVID. I'm Imtiaz, and today I'm going to be talking about some really interesting work we're doing regarding generative models and uniform sampling from their manifolds. We call it MaGNET for short, which is short for Maximum Entropy Generative Networks. Oops. Oh, I think click, yeah. Okay. Generative networks are ubiquitous nowadays. It's being used in so many different domains. I'm pretty sure a lot of us in this room are using it for our own work. It's being used for super realistic face image generation, super resolution, audio synthesis, text synthesis, and even X-ray image generation for diagnostic applications. One thing that's common for all of these applications is that these generative networks are used to fit a data distribution that is given in terms of discrete points in a data set. So when we have a high-dimensional data set, what happens is that, suppose we have a data set of cat images, 1 megapixel cat images. So if we were able to do a scatter plot of those images in the high dimensions, what we would see is that there's this hypothetical surface over which all of these samples lie. And on different regions of this manifold or this surface, we would see different attributes of these cat images. Suppose for this region, we have tabby cats, and for this other region, we have Bengal cats. And for samples that are of this manifold, it could be anything from our own face images, which are 1 megapixel, because this is a 1 megapixel ambient space, or it could be just noise. So when we say we are talking about a manifold of cat images, we have a surface with all the cat images that are possibly out there. And when we are creating data sets or basically sampling from these manifolds, what happens is that we won't necessarily have an equal number of samples from all parts of this manifold. So tabby cats are more common so for this region of the manifold, we'll have more samples. Bengal cats, less common, so we could have like less variations of Bengal cats present in this data set if we are like scraping from the internet. And this gives us the idea, this gives us an intuition of a distribution over this manifold. So we could say that there's more density around this region of the manifold because there's more sample, and less density around this region because there are less samples. And if we think about a 2D example where we have like a 2D domain, a triangular domain where we are getting samples from, and we perform, because of collection constraints like availability, like we just said, we have biased samples in the training data set, so they're biased towards the edges. We have more denser samples from the edges. If we train a generative model or a GAN on this network, what will happen is that GAN would reproduce these biases. So if I randomly sample this generative model that's been trained on this data, we'll see that it's still sampling denser regions from these edges. And this could have catastrophic consequences in case of fair image generation or data augmentation, or even downstream applications that depend on these generative models. Because if this generative model is biased, then downstream applications would also get biased in a sense. So what we propose is a provable method to sample uniformly from any pre-trained generative network. So we train this GAN on this biased data set, and regardless of the training distribution, we have a method to make the output distribution of this generative network uniform. So when we use MaGNET or maximum entropy generative network sampling on this GAN, we get uniform samples on the domain of the original data. So to understand how this works, we need to step back and go back to the continuous piecewise affine ideas of deep neural networks. Even though they're more explored for deep neural networks, they're easily translatable for the deep generative networks as well. So what this says is if we have a generator that has piecewise affine activations, like leaky ReLU, or has max pool layers in them, then we can express this generator in an expression like equation 1, where the expression is in terms of A omega and B omega, which are the slope and offset parameters of the affine partitioning that this CPA induces. To visualize what's happening here, suppose we have a generator that takes in a 2D vector from this square domain and then translates it to a 3D space. What would happen is that the CPA is inducing a partitioning in space, and for suppose like the samples that are from this partition, where the star is, there would be a single set of affine parameters that tell me how these samples are going to be translated to the 3D space. And this intuition gives us the ability to derive explicit expressions on what and how any input distribution P of Z is gonna, like how it's gonna be transformed to the output distribution, PG. So in theorem 1, what we propose in words, this would be that for any input distribution, the P of Z, the output is just an affine transform of the input distribution, which is weighted by the volume scalars of each of those affine regions. Now, using this expression, what we can do is, suppose P of Z for a generator was Gaussian. We can find out what the output distribution is going to be for a Gaussian prior. It could be a uniform prior as well. And what we can also do is we can find out what P of Z we would need to be able to get uniform in P of G. So, and this is what MaGNET does. So simply speaking, if we want K uniform samples from any pre-trained generator, we don't need to train it again. What we just need to do is sample it n times, where n is sufficiently bigger than K. We need K uniform samples from the generator. For every Z, or every latent vector that we sample, we estimate the volume scalar. And then we use the volume scalar to sample with replacement the latent vectors. And this is exactly what we're using to get uniform over here. For both of these images, we have the same number of samples. So apart from the 2D example, to understand what MaGNET does in high dimensions, what we do is we take a state-of-the-art variational autoencoder called NVAE that is trained on MNIST. And what we do is for every MNIST samples, we know those samples are on the data manifold because it was in the training data set. So there's points on the data manifold. We consider a region of epsilon radius around that point. And we count the number of samples that are generated by standard sampling of the GAN, of the NVAE, or MaGNET sampling of the NVAE. So over here on x-axis, if you look at the numbers, what this number represents is that for some MNIST samples, or some points on the manifold, we have up to 400 generated samples when we are using standard sampling. Whereas for some MNIST samples, we have 100 generated samples. So there's a large variation in the density for different regions on the manifold. Compared to that, MaGNET has a very small variation of density, which kind of indicates that MaGNET is producing uniform samples for even this high-dimensional MNIST data set. Apart from that, we also do experiments on uniform phase image generation for state-of-the-art StyleGAN2. So what we do is we take a pre-trained StyleGAN2 that has been trained on Flickr Faces HQ dataset. StyleGAN2 has this, like these style-based generators, they have this mapping network and another like synthesis network. So there's this notion of a style space that's an intermediate space, and then there's a notion of the pixel space where the output images are going to be. So what we do is we use MaGNET to be uniform on both the pixel space and the style space. And over here, the bounding boxes, the red and green, are based on Microsoft Cognitive API predictions for gender. And what we see is that when we're making it uniform for the pixel space, we have more presence of different accessories that the faces are wearing. So we have more sunglasses, more caps. So this is a smaller batch. We have larger batches in our paper. And also, we have attribute distributions for like a very large set of samples that we would like urge the audience to take a look at. And the most interesting bit is when we're using MaGNET on style space, so uniform over the style space, through this method, we can reduce the gender bias of a StyleGAN2 by 41%. So we have a pre-trained StyleGAN2 that generates 67% female when it's like sampled naively. But then when we use MaGNET to make it uniform, no retraining, no labels required, we can like reduce the gender bias. And we can also increase the fidelity or the quality and diversity of these samples based on precision and recall metrics by 3 and 4.1%. So this definitely shows that there's some utility in using MaGNET in these like state-of-the-art models to like mitigate gender bias or balancing out attributes. Another interesting examples set of examples that we see is when we use MaGNET to be uniform on the output dimension on the manifold of a prog-GAN trained on CelebA HQ dataset. So what's interesting here is that if you look at these, oh wait, somehow it's starting to work. And okay. Yeah. So what you see here in these images is that, so for this image over here, you see that there's a fusion of attributes. The upper part of the face has fairer skin tone compared to the lower part. And the upper part has some sense of feminine attributes compared to the lower, where we have bared. So, and this can be seen in some other samples as well. So these samples are not present in the data set at all. And these are not generally sampled when we do a naive sampling of prog-GAN. And these are basically coming up when we are using uniform sampling, because uniform sampling is making the probability equal all over the manifold. And these images, which are in between different attributes that we generally see, would necessarily be samples that are in between these well-approximated regions on the GAN. We do conditional generation for ImageNet, and I'm just going to speed up a little bit. So on the left set of images, we'd see for standard sampling, these are conditioned on the SAM08 class. So just one class. There are other classes samples in our paper. And if you look at the right set of images for MaGNET, we'd see that there are larger variations in the backgrounds. There are humans coming into the picture, even though they're not that well formed, because the GAN is not trained to generate humans in these regions, when it's conditioned for SAM08. And one interesting insight that we could give about this is this could be a way to kind of assess GANs in a better way compared to just naive sampling. Because when we are doing MaGNET sampling, we are sampling from the whole span of the generator, compared to when we are doing naive, we are sampling from closer to the modes where the manifold is better approximated. So this could be, MaGNET sampling could be a way to assess how well the manifold is approximated between different generative models. And we also show in our paper that we can use MaGNET to do manifold geometry estimation, like for example, Lipschitz constant estimation. And when we are using uniform samples from the manifold to estimate these the geometry coefficients, it's more faster to converge compared to standard sampling. So to summarize, we present MaGNET, which is the first provable method to sample uniformly from any pre-trained generative network. This works for state-of-the-art models, we've shown that, and for multitudes of data sets. And our method also shows promise for StyleGAN2, where we can balance the attributes out. And MaGNET can also be used for manifold coefficient estimations. So please check out our paper at MaGNET Splines, short link for you guys to check it out. And I would be taking questions now. Thank you so much.